So this is a quick look at my metal detector circuit, which basically uses an inductor to detect with variable inductance the presence of ferrous metals nearby. This is for the metal detector mini project, and going over the schematic and components and calculations. The basic schematic of my circuit looks like this. So it has the relaxation oscillator topology with now an inductor in series with the capacitor, and that allows for the fluctuation to happen in the oscillation based on the inductance. So the way that this looks on the circuit itself is, because this is a LM311, not a 358 as was linked in the document, the pinout looks a little bit like this. So VCC plus has positive 5 volts, VCC minus has negative 5 volts. The emitter is shorted to the negative input, and the collector output is the signal output. Balance and strobe the two balance pins are shorted together, and the rest of the circuit is connected into the positive and negative inverting inputs of the op-amp or comparator bit. So that looks a little bit like this. This is a Max 941 test circuit that I'd made to sanity check myself when 311 wasn't working, according to the 358 pinout. But this is what the circuit looks like. We have 100k resistors serving as a voltage divider for the positive terminal of the comparator op-amp. We have a 1k pull-up right here between the collector output and positive input, and the operant capacitor and resistor are a 1 microfarad capacitor and a 1k resistor, which together form the oscillating bit, and the 1 microfarad capacitor is connected in series to this inductor over here. So the inductor I had made using the coil winder in EDS. This is relatively thin gauge magnet wire at around approximately 150-160 turns. The 1 millihenry, that's how I got to 126 turns. The measured inductance was around 2 millihenries on the LCR meter, with a resistance of 30 ohms and a complex impedance that's slightly higher depending on the frequency. So this circuit, with this inductor that I created, has a normal steady state oscillation frequency of around 14 kilohertz. The 470 hertz that we see up at the smaller frequency measurement based on my time brackets is actually the steady state oscillation from the relaxation oscillator circuit. So that is the value that we get from just the RC. And then the inductor pushes that up to a higher frequency, which we can see the steady state is around 14.1 kilohertz or so right now. And that's with nothing on the inductor. And the way that we can test the functionality of the metal detector is by introducing ferrous objects. I have an assortment of iron wrenches and an aluminum wire snipper, and estimated inductance based on the iron core can go up a couple times. Measured inductance with, for example, a pair of scissors or one of these needle nose pliers went up from around 2 millihenries to the largest was about 3 millihenries on the LCR meter. And that actually causes a change in the frequency of, and I have this pretty far away, and I'll move it in over here. So as I bring it closer to the inductor, the frequency goes up slightly. And then if I insert it into the inductor, the frequency actually goes up to 15 kilohertz. And then that's with just a pair of needle nose pliers. I can add some more iron and redo that. So with these three things, the frequency goes from 14 kilohertz to a larger 16, 17 kilohertz, which successfully detects that metal. And again, if I take it far away and just bring it close by, the frequency does change by a little bit. But really the greatest inductance shift happens when you make it almost like an iron core inductor by putting it into the middle. And I can repeat that with some objects that are not ferrous. So for example, taking a look at the wire snippers, we're back to a steady state of around 14.1 kilohertz. And then taking the wire snippers close by, we have a similar frequency, very slightly higher, and then actually inserting it gets us to 15 kilohertz. So that's the functionality of the metal detector. And we have the capability to successfully detect these pieces of metal based on the frequency shift that is occurring on the signal generated by the circuit measured at the oscilloscope. So, cool functionality, a lot of things learned. Some interesting behavior of the circuit, for example, is if you actually disconnect the inductor from the capacitor, so now this is just not even connected to ground, we actually get a very high frequency oscillation of around 1.4 megahertz in this case. And if we zoom in time-wise, this actually looks like a clean, full signal. And after talking about this with Joe, we came to the idea that this is probably because of some very small capacitance that's probably present in the breadboard itself, because the way that the headers are essentially small capacitors. And so that sort of self-oscillation is throwing us off a bit, because when you don't have anything connected, it still has this oscillation. And actually with much smaller values for the capacitor, you don't even see this relatively larger frequency signal, like the 14 kilohertz. Instead, all you get is that very high frequency signal. The oscilloscope has a hard time picking up the smaller signal. But all in all, this is a functional metal detector with a steady state frequency of 14 kilohertz, and it functions just as this oscillator should. Thanks for watching.